Hello, everyone. For the last session, we are going to discuss nuclear magnetic resonance spectroscopy, NMR spectroscopy. NMR technique is very useful these days. Actually, it's a common technique these days. We can determine the structure of an organic compound and useful for identifying the hydrogen skeleton to which the functional group is attached. We can use a small amount of materials to identifying. It's a non-destructive test, and large amount of information can be obtained. For example, number of the protons in molecule and relative position in the molecule. Different nuclei can be measured, like carbon, fluorine, and phosphorus. Proton NMR allow the uh, quantitative and quantitative characterization of different types of hydrogen in the molecule, and CNMR identify the carbons of the skeleton. These are two different uh, NMR that we can do. So as you see that each nuclei has a spinning, and you see the spinning charge because of the spinning, and here we have the positive half for one and negative half for one. The magnetic field generated by a nucleus of spin positive half and is opposite in direction from the generated by a nucleus of spin negative half. And so you see that they have a different directions. So, and they are distributed in the materials. But when we apply a magnetic field, all of them are directing toward the one um, direction. And the energy difference between the nuclear spins can be defined as the frequency of adsorbed spectroscope electromagnetic radiation is proportional to the energy difference between two nuclear spin states, which is the proportional to the applied magnetic field. So the frequency of adsorbed electromagnetic radiation is different for different elements. And you need to know that NMR is concerned with the change in the direction of spin orientation. That's why we call it nuclear magnetic resonance. And the frequency of absorbed electromagnetic radiation for a particular nucleus like proton and carbon 13 depends on the molecular environment of the nucleus. So here we have a term that we call it nuclear shielding. If all the protons were exposed to the same magnetic field, they would absorb at the same frequency. Actually, when a molecule is subjected to a magnetic field, the bonding electrons circulate in such a way as to generate additional weak magnetic field of their own. In general, these new magnetic fields oppose the large, fixed magnetic field, which has the effect of the particularly shielding the underlying nucleus. The greater the shielding, the lower the frequency required to produce resonance. So chemical shift is a measure of the degree to which a nucleus in the molecule is shielded. And protons in different environments are shielded to greater or lesser degrees. They have the different chemical shift. Reference standard, highly symmetrical tetra methyl methylsilan, protons of which are more highly shielded than the proton of most other organic compounds, which is the reference standard. So you see the upfield and downfield, increasing shielding in upfield and decreasing shielding in downfield. So we have the zero for the TMS that we defined, and you see that here are the electromagnetic substitute decrease the shielding of methyl group. See how they are different. So here you see difference between CHCl3, CH2Cl2, and CH3Cl. So for the first one, we have a CH3Cl that we have with a greater shielding, and then CH2Cl2. We have weaker shielding for that, and then we have a Cl3 at the end that it has the lowest energy of the shielding. Protons attached to sp2 hybrid carbon are less shielded than those attached to sp3 hybridized carbon. That's why we have such a difference for the previous example. So here you see that we have the 2 sp3. That's why it's very strong. And then we have a CH2 with the sp2 hybridization, so it's with the lower energy. And at the end, we have a sp3 sp hybridization, so you see it's very weak. Information that we can obtain from NMR spectra is that from the number of the signal, how many different types of hydrogens are in the molecule, position of the signals, what type of hydrogen, and relative areas under signals, how many hydrogen of each type that we have, and splitting pattern, how many neighboring hydrogen that we have. So these are the examples that we are going to discuss about. Positions of the signals are shown as you see in this table. Primary is going to be seen in the zero point 0.9 ppm, and then secondary, tertiary, aromatic, and so on. So you need to notice that these numbers are important for the future reference that we want to uh, identify the compound. Here is the proton chemical shift range for the different compounds. For the first example, you see that we have a toluene. It has a two different hydrogen, hydrogen in the A side and B side. So we have a two peaks, A and B. You see that for A, we have the in the lower range, and for the B, which is a weaker, we have the in higher range. And here are the chemicals shift. These chemicals, they have A and B different locations. For example, the cyclohexane, hexane, all of them are A. So here are the again we just identify A and B and C for each compound. It's showing the how many different peaks that we are gonna see in the NMR spectra. So in integration or relative area under each signal, how many hydrogen of each type. So you see that we have A, B, C types of hydrogen. For A, we have a 3A, a 3H. For B, we have 2H, and for C also we have a 2H. These are different types of the hydrogen signals that we are going to see in the and again you see that we have a 12H for the cyclohexane. So we have a 6H for a cyclohexane. These are the answers for that example that we told. So here is this splitting. For the splitting, we just need to differentiate between two signals that they are very close together. So for the cyclohexane, as you see, we have a one signal. There is no splitting for that cyclohexane. And also for the 2,3 dimethyl, 1, 2 butane, we have 12H. It's a singlet, and we don't have any. For benzene also, it's a singlet, uh, 6H. There is no, but we have for the uh, xylene, we have two different uh, group A and B, and you see all these examples. For ethyl benzene, you see we have a three peaks because it has a three different types of hydrogen. And again, we have a triplet, quartlet, and singlet for ethyl benzene, as you see, A, B, and C. C is for the cyclohexene. And this is the another example. See that. So for the NMR after benzaldehyde, you see that we have a uh, three peaks. If you can say, one peak is for this H, which is connected to CO double bond. This is the lowest energy hydrogen. And then we have three three hydrogen, two hydrogen actually connected to the C double bond, and those are seen with the 7.89, and the other are seen in the lower range. This is another example, and you see that this example is showing you how many peaks we are going to see for each part of the compound. So at the end, we are going to show you about the CNMR, number of the signals, how many different types of carbons, splitting, number of the hydrogen on the carbon, and chemical shift, hybridization of the carbon, sp, sp2, and sp3, and chemical shift is showing the environment. At the end, this is the example for C13 NMR that we have four different carbon. So that's why we have four different peaks. CH3 as a CH2 as a C, and CH as a D, and CH3 again the other side, because this is asymmetric. So A and B are different. So as you see, A and B are separated in the graph, and this is the C13 NMR. Thank you for uh, considering this explanation.